Good afternoon, everybody. Welcome to another exciting Monday afternoon, cold but sunny Monday afternoon of Chem 170 Organic Chemistry with your host, me, Dr. White. Hopefully you had a good time since we last met. It's getting winter out there. I don't know if you saw the forecast, but they're talking like 1 to 2 inches of snow tomorrow, which means when I'm through my class today, it's out to the garage, fill my snowblower with gas and fire it up while it's still nice and warm. I always do that. I also have a shovel. If it's only 1 inch or so and it's powdery, I'll take the shovel. I could use the exercise. All right, let's get going. Today's game plan. First, I will go through test number 3 answers, which I will cut out of the video. But if you need to see the answers, feel free, to come to my office hours on Tuesday and Wednesday from 6 to 7:15. If you can't make it to my office hours, email me, and I'm sure we'll be able to find out a time where I can set up a Zoom meeting to meet with you so we can go through the answers for test 3, because I am cutting it out of the video. How do you like my special effects there? Oh, I see someone doing it too. All right, let's get going. And you all should have received an email from me over the weekend with And with that, I'm done going through test number 3. Remember, I'm going to be cutting it out of the video. I can do the same time. I'm ambidextrous. Oh, they clash. But anyways, if you need to see it, come to my office hours or email me and I'll set up a Zoom meeting with you. All right. Now, any questions about test 3? Well, if I were in your shoes, I'd have a question. Well, we've had 3 tests and a good part of the semester is done. We're in week 13 of 17 weeks. Wow, where does the semester go? Boom. Time flies when you're having fun with organic chemistry and Dr. White. But anyways, what's my grade now? Everybody see what is my grade now? Thank you. All right. There are 2 ways you can do this. You should calculate the number X, which is the sum of your 3 test scores divided by 3. If X is 90 degrees, 90 or higher, then you're getting an A. This means equal to or greater than 90. If X is 80 to 89, you're getting a B. If it's 70 to 79, C. 60 to 69, D, and less than or equal to 59, F. Now that's method 1. Now, if you look at my syllabus, you're allowed to drop one of your tests. So let's look at method 2. Method 2 is y is equal to the sum of your two highest tests divided by 2. And once again, if y now is 90 or greater, you're getting an A. If it's 80 to 89B, 70 to 79C, and 60 to 69D, less than 59F. Now, this is based on one important assumption. You've handed in all the labs. If not, it's a much more complex way. But the reason I can ignore the labs if you handed them all in is lab scores, the way I grade, usually keep your grade the same or increase it slightly. Because I don't grade my labs that hard. I'm not going, ooh, how can I take points off? No, it looks right. I'll give you points. Any questions on this? All right. In that case, let's get back to work. Now, we were talking about fats and oils. Remember, fats and oils are triglycerides, triester. I already wrote it, I'll write it again. All fats and oils have this general structure of triglyceride, three esters, ester number 1, 2, 3. Everybody got a copy down? Good. Now, for tallow, which is beef fat, which you should know, and white grease and yellow grease, two different grades of pig's fat, which you should know. I came up with approximation, the structure of either tallow, white grease, or yellow grease. It's roughly a 50-50 mixture, but when you have three like this and only showing one structure, I do this. And this is a structure for tallow, white grease, and yellow grease. Now, oh, I should make you have some fun, not make, enjoy. And the question would be, what's the products, three of them, three products, three different products that you get from that reaction. and give me a thumbs up when you're done. And don't forget, hand in your labs. They're easy points if you hand them in. Otherwise, you get 0 if you don't. And I caught up this weekend. You look at D2L, and all the labs that were handed in as of Saturday morning have been graded. All right, we'll wait for everybody to finish. Thank you, Ignacio. And everybody's finished. We look here, what do we have that's different? 1 ester, 2 esters, 3 esters. And this is acid hydrolysis of an ester. Fats and oil chemists write it backwards. So ester number 1, you'll get this alcohol, plus notice what's R prime, R sub S. You'll get stearic acid. Ester number 2, you'll get this alcohol, plus what's R prime, R sub O. You'll get that. And finally, ester number 3, you'll get this alcohol, plus this part will give you stearic acid again. If you want to put a 2 there, you can. You don't have to. And notice we have glycerin, stearic acid, and oleic acid, 3 different products. Now, just to remind you, what's the structure of stearic acid? Now, on a test, if I ask like this, then you can use the abbreviated RS, sub S. If I ask you draw the structure of stearic acid, don't use R sub S because I'll mark it wrong. And you should know the structure of stearic acid, 18 carbons. It's a saturated fatty acid, no carbon-carbon, double bonds. And this part here is what we mean by R sub S. And right here, this is oleic acid. Now, when I have R sub O, R sub S, you use abbreviation. But if I were to ask you draw the structure of oleic acid, and this is the structure. So again, got 18 carbons, but notice that carbon C9, there's a double bond that can be cis or trans. And what we mean by R sub O is that. Now I talked about, well, wait till everybody's done writing. Everybody done writing? I talked about hydrogenation of fats and oils. Remember, you learned a long time ago. Take a double bond, 1 pi bond, one sigma bond, hydrogenated hydrogen in the catalyst. Catalyst could be nickel, platinum, or palladium. You break the pi bond, and each carbon gets a hydrogen. If I were to take an oil, which is high in unsaturated oleic acid, and let's use this example. What would be the product or product for that reaction? Your turn. I will tell you this, hydrogen nickel will not react with an ester. And when you're done, give me a thumbs up. And I'm going to give you a hint. Look at what R sub O is. Look what R sub S is. And we'll wait for everybody to finish. Am I nice or what? Don't answer that. All right, my turn. Now, if we look at this fat or oil, tallow, yellow grease, white grease, guess what? The ester will not react with hydrogen in a catalyst. I know I've done this on 40,000 pound batches in an actual chemical plant. I actually got in trouble because I came up with a way to greatly improve this reaction. And the research director in the Netherlands had about 150 chemists and technicians, and they hadn't been able to do it. I had one technician, I knocked it off and did it. He didn't like that. Oh, is he mad? But that's another story. Now, what's the difference between oleic and stearic acid? A double bond. And remember, double bond, hydrogen, catalyst, you break the pi bond, and each carbon gets a hydrogen. So if I take oleic acid and hydrogenate it, I'll get stearic acid. Let's move that A a little farther away. Looks like stearic A. It's not stearic acid. How so? This double bond here becomes CH2, CH2, add a hydrogen to each carbon. So 7 CH2s, 7 is 14, plus 2 more makes 16. And I've got this wrong here. Ooh, I don't know where my brain was then. I had a brain freeze. And you make stearic acid. So what that means is, first of all, hydrogen will not react with the esters. So they'll still be there. But what will change, the R sub O becomes R sub S. The R sub S isn't going to react. And this R sub O becomes R sub S. And that's how you make hydrogenated fats and oils. And like I said, when I was at Unichem, I actually supervised this reaction in a chemical plant. Everybody got a copy down? All right, if I look at the clock, instead of rushing to the next section, which is going to take a while to talk about, let's take a 5-minute break. If I look at my clock, come back at 1:52. And that way I won't have to rush for the next thing, which is probably one of the most important things I'll teach you this semester. Plus, it'll be show and tell. I'll see you in 5. I'm going to get up and stretch. I'm back. I had to get my show and tell. Almost forgot it. All right. Now, what I'm going to talk about next is probably one of the more important things I'll teach you this semester, not only for your grade, but just to learn for your daily life. And that's, how does soap work? Now, have you ever thought about it? You get some dirt. Well, my hands are clean, but pretend I got dirt on here, or grease, or even worse, greasy dirt. Years ago, I was watching TV and there was a commercial and it said, our product is so good, it even cleans greasy dirt. And I just started laughing. But anyways, you got dirt on your hand and you try and get it off with water or grease, it's still dirty. But if you use that magic stuff, soap, well, let's see, can everybody see it? Soap, bar soap, or the liquid soap, I was going to bring that in here, that's in the dispenser, and then water, you go like this, put it under the water, your hands are clean. What's going on? Well, it's organic chemistry. Yes, it's organic chemistry. Let's look into soap and how it works. Now, being Monday, I should be subtle. Everybody get the message? And know this. And what is it you should know? How soap works. Now, this is an area I worked for a number of years and I have patents in, not soap particular, but what's called surface active agents. An organic chemist being lazy shortened that name, surface active agents, to surfactants. And surfactants play a role in our daily life in many, many things. The most obvious is how soap works. So what's a surfactant? It's a molecule that has a nonpolar tail and a polar head. And most surfactants, not all, but 90% of them have that type of structure. And they play an important role in many things in our daily life. So let's look at, how does soap work? Well, soap has a hydrocarbon tail, which means the, let's do this, nonpolar tail, which means hydrocarbons, carbon, hydrogens, carbon, single bonds, and a polar head. Now, in my bar soap, the structure looks like this. Now, R sub T is tallow. That means it's a mixture of oleic and stearic acid, or actually the carboxylate. That means it's got 18 carbons with and without a double bond. Some of the chain lengths are a little shorter, but this is a specific soap. Now, the liquid ones are a different structure, but nonpolar tail, polar head. And you should know, what is the general structure of soap. You should know that. Is this coming on? No, it's not what I wanted. All right. Everybody see underneath dial, and they don't have mine. I don't get the antibacterial. I get the spring one. I like the way it smells. Now, everybody see here where it says soap, sodium tallowate, sodium palmitate, sodium cocoate, sodium palmkernelate, aqua, otherwise known as water, tal, coconut acid, palm kernel acid, tallow acid, glycerin, and then it has PEG 6 methyl. Let's see if I can get images and better. All right, see where it says inactive ingredients, and it also has glycerin. Now, the PEG 6 methyl ether is you take methanol, CH3OH, and react it with 6 moles of ethylene oxide. Then it's got perfume, sodium chloride, pentasodium pentanate. That's a preservative. Next one is also preservative. And then color, if it's certain color. If not, you might see titanium dioxide, meaning it would be white instead of this one, which is a yellowish color. Now, the soap is a mixture of different carboxylate anions of different fatty acids. The tallow is 1618, palmate is 16, a little of the cocoate and kernel, those are lower, usually 12 or 14. And the reason they have the coconut oil and this and tallow acid, well, if they didn't convert all those to carboxylate anions, that's why they put it down. That's to protect themselves. Now, how does soap work? Well, it's got the sodium tallowate, which is the main ingredient. And I think I mentioned I worked for a company that made this. We sold it to companies like this, Dial, as these little pellets that were white and looked like soap. And we called them, long before I did, soap noodles. Hold on one second. You see the soap noodles right here picture? How they got the name noodles, I don't know. And whoever wrote this is wrong because it says palmitic. No, it's mainly tallow fatty acid. Well, I wonder, I'll have to write this website and tell them, correct it. All right, let's get back to the important stuff. How does soap work? Now, soap has this structure, non-polar tail, polar head. You should know. Oh, look, I wrote a message to myself. Remember, like dissolves like. Now, there's a rule of thumb. It's on this thumb. Can you see it? A rule of thumb is something that's almost always true, but not 100% true. 100% true, we call that in chemistry a law. But if it's mostly true, we just call it, can't call it a law, but a rule of thumb. And it's like 99% true. All right, let's look at like dissolves like. I'm gonna be real real scientific. And I'll never ask on tests what's like dissolved like. I'll expect you know how to use it. Like dissolved like, polar things are soluble and other polar things solvents. Non-polar and non-polar things are soluble in non-polar solvents. If you mix polar and non-polar together, they're not soluble, which is what we come from, how we derive the name like dissolves like. Now, important thing, what are polar things and solvents? Well, the most polar thing in our world is water. Alcohols are polar, like ethanol or isopropyl alcohol, and salts would be an example of polar. And later on, I'll explain why sugars are polar. If you think about it, if you take ethanol, you can dissolve it in water. If you take sodium chloride, it dissolves in water. If you take sugar, like when I make my tea is mainly water. Now, this you should know. Ooh, now, what are nonpolar things? Well, vegetable oil, fats, and oils are nonpolar. And just to give you a little interesting thing, Vaseline is nonpolar, baby oil is nonpolar, gasoline is nonpolar, and now the important ones, dirt. Yes, dirt has been classified. It's nonpolar, and grease, like stuff you get on your hands. That's nonpolar. So, is this true? How many of you ever seen oil vinaigrette dressing? Ooh, I can go to the internet now. I can spell. I tell you, I was always the first one down the spelling bee and probably would too. Does everybody see the picture of wishbone Italian? That was my mother's favorite dressing. I learned later on how to make it myself, much better than you can buy, but it's quick, it's available. Notice how there are two layers in there, a top and a bottom layer. Well, this is called an oil vinaigrette dressing. And it's oil, vegetable oil, and vinaigrette, which is vinegar, is 96% water. And because water is polar and vegetable oil is nonpolar and light dissolves light, there are two layers, top and bottom. And if you shake it up, put it on your salad, then you put it back down, they'll separate because of light dissolves light. So we have polar water, nonpolar dirt and grease, which is why you can't clean it off because the water being polar won't touch anything nonpolar, and the nonpolar wants nothing to do with the polar water. So what do? All right, let's pretend I have an electron microscope sort of, and on my hand is this little piece of dirt. Now, hint, you should know this. All right, now water won't touch that because dirt is nonpolar and water is polar. And this is where you get the soap. Now, if you do it with soap and water, soap has a nonpolar tail and a polar head. And because like dissolves like, dirt is nonpolar and you got a nonpolar tail, the nonpolar tail will be attracted to the dirt and the polar head will want to stay far away from that. Now, you're going to use a lot more molecules than this one. Now, this surrounds it 360 degrees all around. I'm just putting 4 in. And this, you should know, is now called a micelle. And if you look in my slides, which I'm going to do right now, in your book, they have a nice picture of micelles. Now, there's different micelles, and one with soap are circular. I have a book on surfactants that's a whole book on this stuff. And it's quite a good, I bought it a number of years ago. It's a good book. And if you cut off a segment here where there, see the little squiggly lines? Hold on. Through the miracle of software, each one of these spheres where they cut out a segment so you can see in the center, in the very center is your dirt particle. And the little wavy lines is the nonpolar tail. On the outside is the polar head. And then you have like in a carboxylate anion, CO minus Na plus, those plus charges are the sodium cations, which they show here. Now, this is totally surrounded. They cut out a wedge so you can see inside what it looks like. But where you see this wedge, that would be there, look like this. So it'd be a whole sphere. And this is called a micelle. Now, if you look at the outside of the micelle, what is it? It's got polar heads. So the micelle, I only show 4, but there are a lot more totally surrounding it. The micelle looks polar to water. And water looks at the micelle now and says, micelle, and this is the key to this. In fact, it's so important, I'm going to write it in red. If we were in a classroom, I'd write it about 2 feet high on the whiteboard. It was that important. Water looks at the micelle and water says, oh, you're polar, I'm polar. I know like dissolves like, we're both polar. So let's go down the drain together. And they do. So like dissolves like, the micelle now looks polar to water. It's surrounded the dirt and the water can't see that dirt. All it sees is the polar heads of the micelle. And because like dissolves like, polar things are soluble in polar things, the micelle now goes down the drain with the water. And look, your hands are now clean. Guess what? That's how your laundry detergent works. That's how your dishwashing soap works. They all have non-polar tail, polar heads. Like I said, this is one of the most important things I will teach you. Let's go through it again. How does soap work? Well, you have soap, which is a surfactant, and has a non-polar tail, polar head. I won't ask on a test, but bar soap has this structure. And in a lab coming up in about 2 weeks, I think it's 2 weeks, I'll talk more about hand soap. But same thing, non-polar tail, polar head. And when you have dirt on whenever, like this morning when I took my shower, I was probably one of the few people in Northern Illinois thinking, oh, look at all the micelles I'm making. And I was. Now, remember, like dissolves like. Polar things are soluble in polar solvents. Non-polar things are soluble in non-polar solvents. And the things you should know, most importantly for this class, water is polar. You should also know dirt and grease are non-polar. So water alone will not get those off and clean things. What you need is soap. And you should know the structure of soap has a non-polar tail and a polar head. And now we have our dirt particle. And because the most important piece of this puzzle, and the most important part of this puzzle, everybody got the message, is like dissolves like. And because dirt is non-polar, it attracts the non-polar tail of soap. Not just four, lots of them, forms a micelle. You should know what a micelle is. It's dirt surrounded by soap molecules. And as I showed you from your book, if you had bought the book, here's what they look like. And they cut out a piece so you could see inside, but that wouldn't be cut out. The whole outside is now polar. And now the micelle looks polar to water. Water says to the micelle, I bet you didn't know molecules can talk. No, they can't, but it sounds good. Anyways, water says to the micelle, I'm polar, you're polar, like dissolves like, we're both polar, let's go down the drain together. And they do, and your hands are clean, or whatever else you're cleaning, your clothes, your car, your dishes, your floor, whatever. And that's how it works. And you should know that. Now, interesting thing, this is a micelle. A couple of years ago, it's been more than a couple of years ago, a number of companies came out with a very interesting product called bicellular water. And Garnier, I guess it's pronounced, came out with the first one, and it's called bicellular cleaning. All right, everybody see on the screen my cellular water? And if you notice, it's got water, hexylene glycol, or alcohol, glycerin, alcohol. This disodium cocoa amphithiacetate is a surfactant, non-polar tail, polar head. That has sodium EDTA, and that makes it preservative. The poloxamer 184, and the next one help thicken it up. And really, this is a soap, and the hexylene glycol and the glycerin help it work better. And it does a good job, especially women who are trying to remove makeup or the grease from makeup off their face. And I've been told by my female students in 170 that this is pretty good. Now, when it first came out, I looked at the ingredients, and the funny thing is, guess what? There's no micelles in micellar water. The only time it forms micelles is when you put it on your skin and clean it, mainly for your face. Let's see something. For all facial makeup remover and everything, and it does a good job. It's not cheap either. A bottle of that is $8. Oh, I'll give you a secret. Whenever you can charge $8 a bottle, was this a pint? 400 milliliters, that's less than a pint. I'm selling you a lot of water at $8 a bottle. I'm going to make a lot of money off this, and they do. But whenever you can sell water as the main ingredient and you command a high price like this, you're going to make a lot of money. When I worked in the fabric softener industry, certain companies that were selling the liquid fabric softener that was mostly water, a gallon for $5 or $6, I'm going to make a lot of profits, and they did. So I just wanted to show you how marketing people play games with your brain, where it's a good product. Students who use this tell me it's a very good product for getting makeup off and other things off your face. If you're a woman, I guess, do men wear makeup? I guess they could. You can see I put mine on. Did my nails too, not. But anyways, this is a good product, so I'm told, but you're paying a lot for a little surfactant. And this, you could probably get by with soap and water, but I think the hexylene glycol and glycerin help it work better. And it's a slightly different surfactant or soap. That probably helps. So that's how soap works. Now, when we talk about synthetic, and now I'm going to turn the switch off. If you look at your laundry detergent, it contains what's known as LAS, and that stands for linear alkyl benzene sulfonates. And switch is totally off on this, but I thought you'd like to see more. I better write it here. Most of your laundry detergents, this is the active ingredient, a linear alkyl sulfonate, and the R group is CH2, CH2, et cetera, CH3, 9 to 12 carbons. So this is your nonpolar tail. And this part is your polar head. And this was developed during World War II and actually not commercialized until I would say, mid-1950s. Before that, they used tallow fats, sodium tallowate type products to make laundry detergent. And this does a better job. They also add other things, brighteners and other additives to help it work, but most of them do the same thing. Now, I got influenced by my mother in the way that I used, oh, they changed it a little. Oh, they have sodium lauryl sulfate. That's not right for the others. It's the LAS I told you about. Maybe I'm wrong now. They're more switched to this, and I can understand why sodium lauryl sulfate, but it's the same thing, non-polar tail, polar head. And when you put it in the washing machine, you put your clothes, some water goes in there, put the soap, it agitates it to help mix the two to make micelles. And then when it empties, it goes down the drain. All right, let's move on. Now, next couple slides, click. I'm going to turn the switch. Will this be on a test to the off position? But this is something interesting that I thought you'd like to learn about. But I will not put this on a test or the final. There are a class of compounds called phosphoacylglycerols, and they're triesters of glycerol, meaning glycerin, which two hydroxyl groups are esterified with fatty acid, and the third is esterified with a mixture of phosphoric acid and amino alcohol, and they are called phospholipids, which play an important role in our life. All right, everybody see on there phospholipids from Wiki or Wikipedia? I used to call it, how did I used to call it? Wikipedia. Oh, I pronounced it wrong. My students corrected me. Now, if you look at the structure, forget about the dashes and the lines like that. Here we have one ester. Here we have the second, and the R groups are long. And then on the third carbon, where you normally have a third ester, you have this phosphate ester right here of choline, acetylcholine. And notice it's got a minus charge and a plus charge. That's called amphoteric compound, but it still makes this the polar head. So phospholipids has a polar head, then over here, a non-polar tail. Actually, two of them. And this is the major component in one phospholipid called lecithin. And lecithin has this structure where R is very long. Now, where do you find lecithins? You find them in egg yolks and soybeans. And a while back, a long time ago, I had an idea and I got some lecithin to have one of my chemists work with. And we opened it up. Guess what color it is? Yellow. Have you ever wondered why egg yolks are yellow? Because they contain lecithin, which is a phospholipid. Now, another place you can find a lot of lecithins is in soybeans. Now, one place lecithins play an important role is making mayonnaise. Now, mayonnaise is essentially water and vegetable oil. If you mix two together, just like the salad dressing, they fall apart, they separate. Now, when you make mayonnaise, the classic recipe besides the seasoning is an egg, water, and vegetable oil. Let's see if I can find one. All right, where's the recipe? All right, you see foolproof mayonnaise on your screen now? And the recipe is 1 large egg, mustard, vinegar or water, a little bit, and kosher salt and oil. Now I've seen where they have more oil. Let's see something. I hate when they put these all the way at the end after you have to scroll through. All right, here again, it's a liquid. And I've seen where it has more water or oil in there. And here, what happens? The large egg. Why do you need a large egg to make mayonnaise? Because it acts as a surfactant to hold the water and the oil together in what we call an emulsion. And the lecithin in the egg yolk is what does it, which is a surfactant. Now, again, switches off. All right, now I'm going to tell you a personal thing, and this is just my personal observation. Lecithins, phospholipids can affect your brain and help out by making more choline. And I have found personally, when I eat more soybeans in my diet, I sleep better and I think clearer. So I try and always include soybeans. If you look in my freezer, I have cooked soybeans that I cook, the whole ones, and I'll put into soups or just have that with some navy beans that are cooked and some other stuff, and that will be a meal. And by having that extra surfactants from the lecithin, a phospholipid, it makes my brain work better, which is a good thing. I think so. And I sleep better too, which is a really good thing. And let's see if I can find. And I buy this type, the peeled. Can you see that? Safety Joy. Now, recently because since the pandemic, the price of everything, as you know, has gone up. And what I have found is if you have one near your house, and luckily I do, Amazon's fresh food store, they sell their own brand, which is a lot less expensive, but just as good as Tasty Joy. I've been buying this stuff for, I don't know how many years now, at least 15, 20 years. And what I do, the instructions, you boil it, put it in boiling water for about 5, 6 minutes, take it out, then you can use it in anything. After I boil it, I spread it out in a Ziploc gallon bag, freeze it. I can just take some out, put it into whatever. And a dangerous thing to make, dangerous because it's not low cal, is you take a pound of these that have been cooked, cooled down a little, put it in a food processor with some vegetable oil and seasoning, salt and pepper and garlic powder. If you want, I also sometimes now lately have been putting in a couple of cloves of garlic, and you get this nice paste or spread that you can freeze and take pieces and put it on things like with rice or beans or whatever. It's dangerously good. Plus, the soybeans are good for me too. All right. Now, if we go way, way back, I mean, way, way back, beginning of this chapter, I talked about lipids. And I talked, there were two types of lipids, saponifiable lipids, those that can be hydrolyzed under alkaline conditions to yield the salts of fatty acids plus glycerin, carboxylate anions, and you knew that as fats and oils. Now there's another type of lipid let's talk about, and that's non-saponifiable lipid. And non-saponifiable lipid, say that 5 times quickly, no, don't. But anyways, does not undergo hydrolysis in alkaline solutions. It doesn't react with base and water. Well, now's the time to find out what I'm talking about. And non-saponable lipids are your steroids or hormones. Now, these are lipids that cannot be hydrolyzed with base and water. And they all have this basic ring skeleton. 6-membered ring fused to 6 to 6 to 5. All steroids have this ring system, meaning your hormones. Switches on. And you should know how to draw the ring skeleton of a steroid. 6-membered ring. Next door, another 6-membered ring that's fused at 12 o'clock high, another 6-membered ring. And then next door to the third ring, a 5-membered ring. And let me change my palette because I'm looking like it's leaning over. All right, let's get this again. And let's try that again. 6-membered ring. Next door, a 6-membered ring. Up on top here, another 6-membered ring. And then next door, a 5-membered ring. So you have 6, 6, up here 6, and then 5. You should know how to draw this. If I ask on a test, 3 points, draw the ring skeleton for a steroid, there it is. Everybody got that written down? All right, let's go out to the internet. Bear with me for a second, or maybe more than a second. That's not what I wanted. That's what I wanted. All right, everybody see testosterone on your screen? And here's the actual structure. And notice you have this called the A ring, B ring, C, and D, 6, 6, 6, 5. You don't have to know the structure, write it down, of testosterone. Now, I'll teach you next chapter what this dash and wedge means, but the end of this wedge, where there's nothing, that's a methyl group, up here, methyl group. Notice in the A ring, carbonyl ketone, got a double bond. This is called, the 5-member ring is called a D ring. You have an alcohol. So this is a male hormone, testosterone, which does a lot of interesting things in my body and your body. And now, well beyond my knowledge of the human body, because last time I took biology was freshman year high school, which was a long time ago. There's nothing wrong with biology, but by then I wanted to be a chemist. Now, an important female hormone is progesterone. And notice it's similar to testosterone, but in the D ring up here, instead of having an alcohol on the 5-member ring, you have a ketone. So this is progesterone, and it's an important female hormone. And this, you can see, has an important role in a woman's body. Example, development of breast tissue and other things dealing with a woman's reproductive area. And you can go look at this on your own if you're interested. Now, have you ever wondered what's the difference between men and women? And isn't it obvious? Men are alcohols and women are ketones. Doesn't that explain everything? Men are alcohols and women are not? Nah, not really. All right, now, one thing I should want to mention now, I can go a couple minutes over, and we'll take our break, and that is, I'm going to talk about something right now. In no way am I taking any kind of moralistic view on what I'm going to talk about. It just deals with organic chemistry. And an interesting, another very important steroid hormone is this, estradiol. Does everybody see estradiol? It's got a benzene ring and an A ring, 6-membered ring, with a hydroxyl group. This is a phenolic ring. Here we have our 6-membered ring, another 6, and the 5 up here is an alcohol. And this is called estradiol. And this is the molecule, the hormone, the steroid that regulates a woman's menstrual cycle. And interesting thing, and I've never looked up the history who did that. Long time ago in the 1950s, organic chemists working with medical doctors found that this molecule, ethinyl estradiol, where instead of having in the 5-membered ring OH, you also had a triple bond. That's what this is. A woman's body thinks this is estradiol. Now, estradiol, this one is very expensive to obtain, very expensive. But the precursor, you do a Grignard type reaction with a triple bond on a ketone in the 5-membered ring, and you'll make this. And doing that, the precursor is cheap, the reaction is not that expensive, and I can make this quite cheaply or inexpensively. Well, that allowed scientists to develop the birth control pill. And the birth control pill, if you've ever seen pictures of it, and if you notice, let's do images. See, I have the packaging on the screen where a woman takes one a day, each day of the month. Well, what's different is the amount of ethinyl estradiol, and it keeps it at such a weight that it inhibits a woman from getting pregnant. It forces her body by having different levels of ethinyl estradiol, which a woman thinks bodies think is estradiol, to make her go through her regular cycle, and that's the way she can't get pregnant. Now, are you for or against birth control? That's not the issue here. Because of organic chemistry, an organic chemist, and the fact that they found out how to make this that a woman's body thinks is the estradiol, but is really ethinyl estradiol, quite inexpensively, they're now birth control pills for many years now available for any women who want to have it, assuming it's legal in your state. So far, it is in the United States. Thank God we had our election results, but I don't want to get into that. But this allows a woman who wants to control her body to determine whether or not she's getting when she'll get pregnant, which is a very powerful tool to give freedom to women. And that's affected a good part of our population throughout the world to have that control. That's my personal opinion, and that's due to organic chemistry. All right. Well, guess what? We finished a chapter. That's the end of this chapter on fats and oils, lipids. And next Monday, let me give you some time. Next Monday, I will go through the fats and oils or lipids problem set. You should keep up because that's going to be on test 4 coming up in a couple weeks. With that, let's take a 5-minute break, come back at 2:55, and we'll start something new. And I will warn you, it's going to be really sweet. See you in 5. Let's get started again. Sorry about the late. Something came up I take care of. But anyways, it's new chapter time. It's talking about some new stuff. But remember my promise, except I'm going to break it a little bit, but not much. No new functional group chemistry. So what's this new chapter? Well, first of all, I got to open it. All right, I'm ready to go. All right, everybody see, did I tell you Zoom put a new thing in finally? But I still don't trust them. Everybody see chapter 18? Good. All right, now this chapter deals with biochemistry. And for some reason, people think, ooh, biochemistry, it's magic, pooky, pooky, poo. No, it's organic chemistry. And biochemistry is just dealing with chemicals found in things that are alive, like you, me, animals, whatever. And the important thing, the functional group chemistry that you've learned for organic molecules occurs just the same way in bioorganic molecules, except they're a lot bigger and more complex. In other words, the functional group chemistry going on in your body is the same as what we studied. There's no something, ooh, something different is going on because it's in your body. No, a ketone is a ketone. A ester does what esters do, nothing new. Now, what I will tell you, and now I'm going on well beyond my knowledge of biochemistry. How many of you have heard of enzymes? Those are really catalysts, very fancy, specialized catalysts. Not all, but many of the enzymes are really a very sophisticated way of Mother Nature bringing H plus to the table. In other words, a lot of enzymes are very sophisticated acid catalysts. But let's get on with biochemistry and carbohydrates. Now, this chapter will deal with carbohydrates. Be careful, it might be fattening, you know, put on a few pounds, but let's get into it. And a biochemical substance is a chemical found in something that's alive, nothing different. All right, switch is on. Click. Let's talk about carbohydrates. You should know what is a carbohydrate. And I'm talking about the definition. What is a carbohydrate? A carbohydrate is a polyhydroxyaldehyde, a polyhydroxy ketone, or ketones, or compounds that yield such compounds upon hydrolysis. So if you have a molecule, poly means many, hydroxyl is OH group aldehyde, or as a ketone, those are carbohydrates. Or if it's a molecule that when you react it with water, usually acid catalyst, produces polyhydroxyl aldehydes, polyhydroxyl ketones. Now, one thing my software and sugar chemists do, synthetic organic chemists write their aldehydes this way. And if you go back and look at the slide, you can write it this way. This is an aldehyde. This is an aldehyde. And my software for sugars and carbohydrates likes to write it that way. Now, here I have two sugars or carbohydrates. You do not have to write these structures down. I will give them to you. You don't have to memorize them for my test number 4 or the final. But I do want to talk about them. Now, these are called Fisher projections. And Fisher projections, every intersection of a line is a carbon. Now, it shows stereochemistry, and I'll talk more about that later in this chapter. But if you notice this glucose, you have an aldehyde at the top. Ooh, carbon with a hydroxyl group, another carbon with hydroxyl group, a third carbon with a hydroxyl group, a fourth carbon with a fifth one. Well, I would say 5 is many, so this is a polyhydroxyl aldehyde. And glucose, by that definition, is a carbohydrate. Now, one of the things you've got to learn or unlearn, most people think of the starches as carbohydrates. You know how they say carb loading? I'm sure you've heard that term. Well, guess what? The true chemical definition of a carbohydrate also includes glucose, which is definitely not a starch, but they're interconnected, and I'll show you why later. Now, the other one, now this is an aldehyde. Now here can be poly, many, hydroxyl, OH, ketones. And a ketone, as you learned in test number 2, see how this is all coming together? Now I'm taking out in the real world where it's fun. If you look at this carbon right here, it's got carbonyl, carbons here, and carbons here. This is a ketone, while this one is an aldehyde. So fructose is a ketone with 1, 2, 3, 4, 5 hydroxyl groups. 5 means poly, that's many. So this is also a carbohydrate, and this is called fructose. Now, I'll teach you more about that, but I will tell you this. Glucose is the most abundant carbohydrate, or I'll later call it a sugar, in all of nature. Fructose, a number of years ago, organic chemists, food chemists, were organic chemists, found a way how to make high fructose corn syrup. And fructose is the sweetest of all sugars. I don't know, I think it's even 100 times sweeter than fructose. If I can make it cheap and it's sweeter, I can use less. Guess what? It's now in most of our foods. And let me show you to prove a point. Does everybody see on their screen Coca-Cola ingredients? First one is carbonated water, which means water. And the second one is high fructose corn syrup. And that's what makes it so sweet. It used to be sucrose years and years ago. Once they found a way to make inexpensive high fructose corn syrup, which essentially adding fructose, guess what? That's what they switched to. Because if I'm selling a product and I can bring my direct costs, the cost of my ingredients down, and keep the price the same, I make more money. My profits increase. Let's do one more. I don't know if they've taken it out or not. No, I don't find it. Let's do another one. oh, since coming up with the holidays, how they use cane sugar, maybe because to keep it solid. But if you look at a lot of things, and let's do, does everybody see on their screen tomato concentrate and vinegar? And look, there it is again, high fructose corn syrup. And if you use Heinz ketchup, I guess really pronounced ketchup, but I always call it ketchup. That's how my parents thought, which I have in the house. I also have barbecue sauce, which I like better, but this and is really good. You like shrimp, you take this and horseradish, and you can make your own inexpensive cocktail sauce. See all the neat things I'm teaching in this class? Wow. But anyways, once again, to sweeten it up, high fructose corn syrup. So if you're wondering, why am I learning this stuff? Well, it's in your everyday life. So once again, what is a carbohydrate? You should know. If I ask on test, 3 points, what's a carbohydrate? It's a polyhydroxyaldehyde, polyhydroxyketone, or compounds that yield such compounds upon hydrolysis. Remember, hydrolysis, adding water or adding water and acid. Now, when it comes to carbohydrate classification, and I'll be honest, this is one of the few areas in chemistry I never worked with carbohydrates in a chemical plant or research. In my kitchen, yeah, I work with them all the time. Yes, I make spaghetti, rice, potatoes, eat bread, and the list goes on and on. Potato chips. Did I tell you my favorite are sour cream and Lay's sour cream and onion potato chip, and Doritos too. Those two are dangerous comfort foods, especially the Lay's potato chips. I open a bag and it evaporates like that. Amazing. But anyways, next couple definitions switches off, but you may need to know these for other classes. Now, there's something called a monosaccharide. And that's a carbohydrate that contains a single polyhydroxyaldehyde or ketone. Again, click, switches off. And that's a monosaccharide. An example of that is glucose and fructose. And I'll never ask on tests, give an example of a monosaccharide. But in other classes, they may talk about this. Anybody talk about carbohydrates in your other classes yet? Not yet. Well, if you take some, I know some of the students I've had in the past who have been dietitian majors, nutrition majors, this came up within their classes later on or before they took organic. Now, that's a monosaccharide. Now, oligosaccharide, and I hope I'm pronouncing it correctly. Again, I am not a carbohydrate chemist, even though I'm a chemist who likes their carbs. Trust me, I do. But anyways, carbohydrates that contain from 2 to 10 monosaccharides connected together. Now, how many of you have ever seen a freight train with the boxcars? Well, turns out you can connect these together chemically to make a very long molecule, which we call a polymer, but I'm not going to use that. Carbohydrate chemists don't use that term with their molecules. It should, but they don't. So again, this will never be on test or the final. And you've got me on video saying that, so I can't lie. And I don't. But anyways, carbohydrates that contain between 2 and 10 monosaccharide units are called oligosaccharides. Now, click, the switch is on. There's one special oligosaccharide I would like you to know, and that's a disaccharide. And what I really would like you to know, a you know how you say dimethyl, two methyls? Disaccharides contain two monosaccharides that are bonded together. And what I really want you to know is the most common disaccharide with the common name sucrose, you know as table sugar. And table sugar, the stuff you put in your coffee, tea, or on your cereal, your oatmeal, or when you cook some cookies or whatever, is a disaccharide. And I'll teach you later on, sucrose is a glucose molecule bonded to a fructose molecule. But you should know a disaccharide, sucrose, is table sugar. And later on, I'll ask you to know it's glucose, if I can spell correctly, or fructose, it's glucose and fructose bonded together. So that's your table sugar. But you never thought I'd get into your kitchen or my kitchen or our kitchen. Oh, by the way, shopping tip, the least expensive place I know to get sucrose table sugar is Walmart. For over a year and a half now, year and a half, they sell 4-pound bags and a larger too. And they're usually the lowest price around, even when other stores have it on sale. Their normal price is equivalent or lower. Ooh, that reminds me. Not that I get any kickbacks from this company. I'd like to. Price has gone up. It's gone up 284. Everything's, well, that's inflation for you. But a lot of places, maybe it's not cheaper anymore, but the name brand notices a lot more expensive. Used to be about 250. And if we go to, let's go one other place. Well, I was right. Can you see that? Juul's name brand is $2.99, which is a lot cheaper. It used to be $3.29 when there. And so, like I said, and whether it's an off-brand or Domino or other brands, it's the same chemical. And really, I have not seen a difference in quality between an off-brand and a national brand. All right, sweet, huh? Oh, that was bad. Sorry. All right. Now, there's something called polysaccharides, and it switches again off. Again, you should know sucrose is the name for table sugar. And later on, I'll teach you that that's made up of a glucose and fructose molecule bonded together. Now, there's also what's called polysaccharides. And poly means many, and these are carbohydrates made up of many monosaccharide units bound together. And we have another name for polysaccharides, which we call, and I won't ask you this, starch. And different starches are polysaccharides, where we're talking, I don't know, what's Liga is up to 10, So it's 20, 30, 40 monosaccharides linked together. All right, now, if we were reading the book, I would have skipped chapter 5, and now it's time to go back to that. When we talk about carbohydrates, there's an important concept that now's the time I should teach you. I could have taught it earlier, but now's when you're really going to see it. And that's called chirality. Switches on. If it was a dial that I could turn to 10, I've just turned it to 20. By the way, I stole that from the movie This is Spinal Tap, where the guy said, we're so loud, our music, our dials on our amplifiers only go to 10, but we turn them up to 15. It's a funny movie, strange cult movie. But anyways, chirality. Now, if you look at your right and left hand, they're different. They're not identical. Otherwise, you wouldn't know one's right and one's left. Well, we call this handedness. And carbohydrates exist in two forms, like your right and left hand. They're different. And there's a way we have that. Now, time for Dr. White to get subtle. And you should know the word chiral, which is used in chirality, is Greek for handedness. You should know the word chiral means from Greek handedness. And it turned out, what was it, 3-4 summers ago, it was interesting. I had 2 students who were fluent in the Greek language, and they spoke fluent Greek. And they confirmed chiral means handedness in Greek. I'm glad whoever came up with this didn't pick the Greek word for footedness instead of handedness. That'd be different. But anyways, we're going to talk about chirality, which is like the difference between your right and left hand. And you should know chiral is the Greek word for handedness. Now, when I talk about chirality, I have to bring up mirrors and mirror images. And if you put something in front of a mirror, you'll see an image. And there are 2 types of image. One is superimposable, the other is non-superimposable. Now, I'm not going to ask you what is the definition of a superimposable and non-superimposable mirror image, but you'll need to know that later on. Now, what do I mean by superimposable? Oh, I should warn you. Warning, warning, big warning. I'm going to do some artwork. My mother was a very talented amateur artist. My father was a very talented amateur carver. Both did some really amazing work. I have some still in my house. Unfortunately, they passed long ago, but still, guess what? Not one iota of their artistic talent ever rubbed off on me. So when I'm going to draw some things, if you start laughing, please don't break a rib laughing too hard or fall off your chair and hurt yourself laughing too hard. You've been warned. Now, if I were to take a round ball, oops, it's totally round ball, solid round rubber ball, and I put it in front of a mirror, and this is my mirror. You'll see that image of the round ball. And if I could pick that image out, it could superimpose on the round ball So every point coincided. You essentially push them together in every point. And that would be considered a superimposable mirror image. All right. Don't laugh too hard. Sewing needle. Part in the top of the hole, put your thread, the point. Let's see, I don't know if you can see it. I was doing some sewing the other day. See the sewing needle? Point, out, no. And the part you put the thread in, except I'll draw it this way. Here's my sewing needle. Actually, that's a better one than I sometimes do. And if you put that sewing needle in front of a mirror, and let's make this rounder, you see this image. And if I pick this image off the mirror, I could push it and coincide, every point would line up. And that's superimposable. Now, the other type of image is non-superimposable. That's where not all points coincide when the images are laid upon each other. All right, now I have a homework assignment for you. Yeah, homework assignment, but you don't have to hand it in. I can assume all of you have access to a mirror, either in your home, a friend's home, or if you go to a restroom at a school or wherever, men's rooms always have mirrors. I've been told women's rooms do too, restroom. Now, the homework is take your right hand and hold it up to the mirror. Let's assume the mirror was here. And what you're going to see, I better take my ring off, is your left hand. Your right and left hands are mirror images. There was a mirror here. I go like this. I'd see this in the mirror. And these are mirror images. Now, if you notice, if I get my middle finger lined up, my thumbs don't line up. Oh no. Well, if I get my thumbs lined up, the rest of the fingers don't work. If I get my little pinky, they still call it a pinky, little finger lined up, the rest. So your hands are mirror images, but they're non-superimposable. Oh, I can't resist. Everybody know what this is? A spider doing push-ups on a mirror. I couldn't resist. All right, so you have superimposable and non-superimposable mirror images. And once you learn that, now the switch is totally on up to 25. When we talk about chirality, there are two types of objects. Wow, I'm really being subtle a lot today. And the first object is a chiral object. And a chiral object, and I'll never ask on a test what's the definition of a chiral object, but you should know how to identify objects, whether or not they're chiral. And a chiral object is an object that's not identical to its mirror image, otherwise known as it has a non-superimposable mirror image. Chiral object, non-superimposable mirror image. The other type is achiral. Now, the prefix a in English means without. So achiral means chiral-handedness without chirality. And an achiral object is an object that is identical to its mirror image. It has a superimposable mirror image. So chiral, non-superimposable mirror image, achiral, superimposable. Now, a number of years ago, when I first started teaching this, students were having trouble with this. So someone said, you spelled non-superimposable and superimposable wrong. I said, what's up there? Well, it's super impossible. And that's why they're having trouble, maybe. But anyways, chiral object. That's an object that's identical to its mirror image, or not identical. Let me start again. Chiral object. It has a non-superimposable mirror image. In other words, like your hands. And I'll show you that in a second. Achiral object, it has a superimposable mirror image. So if we go over to our whiteboard, does everybody see 3 points each? Thank you. Are the following chiral or achiral? A sewing needle. Well, how do you find out if it's chiral or achiral? Well, you determine, does it have a superimposable or non-superimposable mirror image? And once again, don't laugh too hard or break a rib. There's my sewing needle. And I'm going to put my mirror in. You don't have to do this, but I wanted to show you how to figure that out. And the mirror image would be this, identical. And this I could pick up and lay over, and they'd coincide when I'd push them together. So this has a superimposable mirror image. That means it's achiral. Let's look at your left hand. Now, is your left hand chiral or achiral? Well, the question is, does it have a superimposable or non-superimposable mirror image? Forget about well, I'll take it off. One of the rare times you'll see me without this on. I've been wearing this since, wow, 1972. My father had one too. I wonder why I decided to do that. I don't know. But anyways, left hand, put it up to the mirror. What do you see? Mirror right here, your right hand. And that's your homework. Check a mirror with your hands. They're mirror images. Here's the mirror image of my left hand. Are they superimposable? Uh-oh, no. If I do my thumbs, nothing else lines up. If I do my middle finger, nothing else lines up. If I do my ring finger, nothing else lines up. So my right and left hand are non-superimposable mirror images, which makes, but first of all, I got to put this back on. Which means your left hand is chiral. Remember, chiral means handedness. That's how they came up with the word, because your right hand and left hand are non-superimposable mirror images. Now, can you keep a secret? If you see a description, right or left, in a description about something, it's going to be chiral. So if I were to say, is your right foot chiral or achiral? Well, immediately I see the word right. I know it's going to be chiral. But if you don't believe me, take your right foot, put it up in a mirror, and what are you going to see? Your left foot. And are they superimposable? No, just like your hands. And therefore, this has a non-superimposable mirror image. Also, the word here gives it away, and that would be chiral. I'm doing a big generation gap thing on you. Think if you had a round rubber ball. By the way, that's the name of a famous song back from the 50s or 60s. Come bouncing back like a round rubber ball, red rubber ball. Well, anyways, it was a good hit. Is that chiral or achiral? Your turn. Remember, chiral, non-superimposable mirror image, achiral, superimposable mirror image. Start drawing. Or if you can visualize it in your head. And when you're done, give me a thumbs up. Remember, achiral, superimposable mirror image, chiral, non-superimposable mirror image. And we'll give everybody time to finish. And while you're doing that, I'll clue you in what I have to do tonight afterward. One, Monday night is garbage night because it's pickup Tuesday morning, and my garbage guys come at 7 a.m. So I always get it out Monday night. And two, if you heard the forecast, and while we're waiting for Andrew to finish up, let's check something. They're saying about less than an inch tonight and tomorrow snow. It's winter. And what I'll be doing right after class, putting out my garbage, and I haven't done it yet, but now it's time for me to do it. I'll fill my snow blower up tonight and get it started because it's warmer out now, and it's always nice to get it started before you need it for the first snowstorm. All right, let's do this one. If I have a round rubber ball, remember, don't break a rib laughing. This I can do pretty good. Wait until Wednesday when I do a four-door car. That's going to really be funny. But I have my mirror. I have my other red rubber ball, and they're superimposable. So it has a superimposable mirror image. That means this is achiral. If I look at the clock, I don't have time to do the four-door car. You'll have to wait until Wednesday. And with that, let me remind you, don't forget hand-in labs. Get them in because they're easy points. I didn't set it up, but you don't want to lose that. And don't forget Tuesday and Wednesday at 6 to 7:15, I will have my office hour. Let me do something. Hang in there for 30 seconds. Oh my goodness, not this week, but next week is Thanksgiving. That's why they got all the turkeys on sale. All right, now the 23rd, at least I'm pretty sure COD has classes until 5 p.m. So I will have my lecture. If you can't make it because you're going out of town, like the Florida or other places, you can still watch the video. I will not this Wednesday, but the 23rd, since COD closed at 5, I will not have my office hour that night. But that's a week and a half away. So I just wanted to remind you. And with that, I'm going to say, if I see you tomorrow night, I'll see you in my office hour if you need help. If not, I'll see you Wednesday. And now I'll say, gang gesund. It's getting dangerous out there. The COVID virus is starting to pick up again in certain places in the United States and heavily in China. I mean, really bad in China. Sad. I hope they get that under control. But that's another story for another class. With that, I'll say, gang gesund, go in health. That's what gang gesund means in Yiddish. And I'll say, bye now. Stole that from Granny to Beverly Hillbillies. And I'll see you on Wednesday.